Okay. So we have completed this particular entire part. So let's start with the new topic, that is the second term syllabus. Okay. Mechanical property of solids. So to define this particular property, let me define you some term. Suppose you have any support from which spring is connected having length L. Now, if you apply any deforming force to this particular spring to compress it till this point or to stretch it till this point, this is the actual position of this particular spring. So this is called mean position. To compress this particular spring towards this direction, you must need some deforming force applied over this particular part. So this is called deforming force. The force which is responsible for deformation of particular object. Similarly, to stretch it, you must need some deforming force along this direction. Now, due to this deforming force, there is change in its displacement, or there is some compression or extension in this particular spring, due to which a restoring force get developed into it along this direction. Restoring force, which will tend to this particular spring back to its original length to come at this particular original position. This tendency of a spring by which a restoring force get developed into it, which tend to bring this particular spring back to its original position, is called restoring or elasticity. Is it clear?
Yes, sir.
So elasticity is simply the tendency of a spring to get or to induce a restoring force into it by which it may attain its original shape on removal of this deforming force is called elasticity. So first is elasticity. Suppose you have a body in which particles are arranged at corner of this particular cube, and in which bond between the particle behaves as spring-like structure, and each corner is being occupied by these particles like this. Suppose there is an element of particle in a particular solid is like this. Now, if you apply a deforming force along any one direction, so it may get deformed like this till this point. Now, due to this deformation, a force get developed into it along this direction, which will tend this particular particle back to its original position. This tendency of body is called elasticity. Is it clear?
Yes, sir.
Okay. So first is the tendency of body to regain its original shape on removal of deforming force is called elasticity. Opposite of this elasticity is called plasticity. So plasticity is the inability of a particular object so that they can't regain its original state on removal of deforming force. That is called plasticity. The inability of a body so that they can't regain its original state on removal of deforming force is called plasticity. The most elastic substance is quartz, most elastic, and similarly, most plastic substances, wax. In general, there is no any object which is perfectly elastic and perfectly plastic. So the property of a body will lie in between elasticity and plasticity. Is it clear?
Yes, sir.
So we can say behavior of body lies in between elasticity and plasticity. Just write it down.
Okay, sir. Done, sir.
Now, this to this deforming force, we may define some term. First is stress. Suppose you have a solid which is attached to this particular rigid support. Now, if you apply any deforming force to it along this direction, deforming force over this particular area of cross section, area of cross section. So this is called stress. The amount of deforming force applied over particular object per unit area to deform it or to elongate it is called stress. This particular body or particle in between this particular term would be arranged in such a way that it behaves like a spring. So if you apply any deforming force to it, there should be some restoring force get developed into it, which tend to bring this particular deformation back to its original state. Is it clear?
Yes, sir.
So stress is the amount of deforming force applied on a body per unit area of cross section is called stress. So stress is deforming force divided by area of cross section. As force having unit Newton and area meter square, so its SI unit will be Newton per meter squared. Now, due to application of this stress or this deformation, there will be change in its length, let's say till this point. Actual length of rod is from this point to this point, and deformation produced is from this point to this point. So if you have to calculate amount of deformation produced in this particular object, so it will be defined by another quantity that is called strain. So strain basically defines your amount of deformation in a particular object with respect to its original dimension. So it is the ratio of deformation produced in a body with respect to original shape. So strain equals to deformed shape divided by original shape. As unit of deformed shape and original shape will be seen, so both unit will get cancelled out. So you'll get strain to be unitless quantity. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Now, stress applied on this particular object and strain developed into this particular object may depend upon one another. So there is a relation to define interrelationship between stress and strain, which is defined by Hooke's law. But there is some limitation or condition for this particular law. It states temperature should be constant and within elastic limit. Why temperature should be constant? So you'll say, if you increase the temperature of a substance, so bond gets weakened, due to which separation between the particle gets increased. So elasticity of that particular substance decreases. That's why temperature of the substance should be constant. Is it clear?
Yes, sir.
So at constant temperature and within elastic limit. The strain produced in a body is directly proportional to the stress applied to it. It means stress applied is directly proportional to strain produced. If you replace this particular proportionality sign by any constant of proportionality, so it will be stress equals to some E times strain, where E is called modulus of elasticity. Is it clear?
Yes, sir.
Now, if you draw a curve related to these two terms, as stress is directly proportional to a strain, so the curve in between them will be straight line. So this is amount of stress applied, and this is corresponding strain to it. So the curve in between them will be a straight line like this. Now suppose this line may incline at some angle theta with this horizontal. So you can say E equals to stress divided by strain, which is nothing but ratio of perpendicular and base. So in terms of graph, it will define you slope of that particular curve. So slope of stress strain graph will define you modulus of plasticity. So you can say E equals to tan theta. Is it clear?
Yes, sir.
Just write it down.
None, sir.
Now, there is some property of this particular modulus of elasticity. First is, what is the physical significance of this modulus of elasticity? So you'll say it defines the elastic behavior of the substance. Greater the value of the modulus of elasticity means greater will be its elastic behavior. So it defines elastic behavior of substance greater the value of modulus of elasticity greater will be elastic nature. Next, it depends upon two factors. First is temperature and next is nature of material. So it depends upon nature of material and temperature. Next, I had just explained you, if you raise the temperature of the substance, intermolecular force between particles will get decreased. So elasticity of that particular substance will decreases. So modulus of plasticity is inversely proportional to temperature. Next is, if you change the dimension of a particular object, there will be no impact on this modulus of plasticity. So you'll say it is independent of dimension of body. Any doubt till this part?
No, sir.
Okay, just write it down.
Done, sir.
Now we have just defined three different terms. First is stress, strain, and then Hooke's law. Now we have certain types related to these terms. First is longitudinal. Suppose you have a rod attached to any support like this. You may apply deforming force to these different body. One would be along this direction to elongate it, and the other will be along this direction to compress it. The amount of deforming force or stress applied to elongate it is called tensile. So this will be called as tensile stress. And the other, in which stress is applied to compress it, so it is called compressive stress. Is it clear?
Yes, sir.
So we may define longitudinal stress in two different ways, whether it is applied to elongate it or it is applied to compress it. So longitudinal stress equals to amount of deforming force divided by area of cross section. So we may define first for longitudinal amount of deforming force applied per unit area to elongate it. And for compressive part, it is amount of deforming force applied per unit area to compress it. Is it clear?
Yes, sir.
Now, due to this application of deforming force, there will be change in its length along this direction, delta L, and in this part, it will be along this direction, delta L. So we may define longitudinal strain to calculate amount of deformation produced in this particular body. So it will be delta L divided by L. Now, if you take the ratio of these two terms, which will be equals to modulus of elasticity, so in this part, it is called Young's modulus. So Young's modulus equals to longitudinal stress divided by longitudinal strain. Young's modulus is denoted by Y. Longitudinal stress is force divided by area of cross section. And corresponding change in strain is delta L divided by L. If you rearrange it, it will be F into L divided by A times delta L. This particular modulus of elasticity is along its length. So it is also called elasticity is length. So Young's modulus is called elasticity of body in length. And in this ratio, as a strain is a unitless quantity, so there will be only unit of stress. So SI unit of Young's modulus is Newton per meter square. And it will have all the property of modulus of elasticity as I have defined above. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Now let me give you a question related to this. A force of 40 kilonewton is applied on a wire having length 2 meters, area of cross section 4 mm square. Find first stress, second strain if Young's modulus is 2 into 10 to the power 11 Newton per meter squared. Elongation produced. Just use the above formula and try to find Ifra, in and out.
No, sir, just sending answer 1 minute.
We have force equals to 40 kilonewton. So for kilo, just multiply 10 to the power 3. And area of cross section is 4 mm square. So if you convert it into meter square, it will be 10 to the power minus of 6. Okay.
Yes, sir, I haven't multiplied the force by 10 raised to the power minus 3.
So stress will be equals to 10 to the power plus 10 Newton per meter squared. Okay, try to solve the other two part.
Yes, sir, fine.
Good, Ifra. Then third part.
Yes, sir, just sending.
As strain equals to delta L divided by L, So you have calculated a strain as 0.5 into 10 to the power minus 1 delta L divided by L, which is 2 meters. So move this 2 to the other side. So it will be 1 10 to the power minus 1. So it will be 10 to the power minus 1 meter or just 10 centimeter. Is it clear, Ifra?
Yes, sir.
Okay. Next is, there will be a question related to string. Suppose a wire is hanged from this support there is a block at this point and another at this point. Let's say this having mass 2 kg and this having 3 kg. So if wires are identical, so you'll be asked to calculate the ratio of stress produced in these two different wires. If wires are identical, then find ratio of stress. Let me define you how to calculate this term. So for a stress, we must need two different terms, area of cross-section and force applied. In this part, the block attached to this particular string or wire will be responsible for application of deforming force. Let's say for this downward block, there will be some force on this due to gravity. So it will be m1 times g. To balance this, there will be some force in this string opposite to this point of contact, which is called tension. Do you have idea about tension?
Yes, sir.
So let's say this is T1. So total upward force, total downward force at this instant will be T1 equals to M1G. And this tension at this point will be responsible for applying deforming force to this string. So T1 will be M1 times G. Similarly, at this point, T1 will be along this direction. Mass of this block is 2 kg, so there will be another force along this direction, N2G. So total upward tension, T2, will be equals to total downward force, that is T1 plus M2G. So T2 will be equals to T1 is M1G, M1 is 3, so 3 times G. So T2 will be equals to T1 plus M2G, and M2 is 2 kg, so it will be total of 5 times G. Ifra, is it clear?
Yes, sir.
So stress on first wire will be force divided by area of cross section. Stress on second wire will be force on second divided by area of cross section. As force applied in this particular part will be due to tension and area of cross section is same. So this term and this term will cancel out. So it will be just equals to FA divided by FB. FA is due to second tension, that is 5 times G, and FB due to 3 times of G. So G and G will cancel out. So it will be 5:3 only. Any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Let's say, suppose you have a wire find ratio of stress in two wires. Try to solve.
Yes, sir.
Ifra, let me define you how you'll be able to solve this. For this arrangement, just try to write this particular term in a vertical manner. So in vertical term, take a support like this, draw a wire, and another wire. There is two force at this bottom term. So there will be a block which must be applying 2F along this direction. So let's say mass of this particular block is 2. Similarly, there will be another block at this point which must be applying a downward force of 3F. So let's say mass of this block to be 3. Total top or upward force at this junction is 5. So if you draw a tension at this term, so it will be T1. Similarly, this will be T1 plus 3F along this direction. So along this direction, it will be T2, which will be sum of these two terms. So at this junction, it will be also equals to just 2T. So T1 is 2 and this 3 on combining, so T2 will become 5F. That's why at this junction, total force is 5F. So this arrangement is equivalent to this arrangement. Is it clear?
Yes, so sir, I haven't arranged it in that manner and that great.
So whenever you have a question like this, try to arrange this particular term in vertical part or vertical manner. Then you'll get idea how to apply stress or amount of deforming force. Okay.
Okay, sir. Yes.
Now try to find. Stress in A divided by stress in B. For A, force applied on A divided by area of cross section of A. So it will be pi r square. Radius is 2, so it will be 4 times r square. Whole divided by force on B by pi r square. So for point A, total force applied is 5F. So it will be 5F divided by 4 pi r square for the first part. FB is just 2F divided by area pi r square. So this pi r square will cancel out. F and F will cancel out. So it will be 5:8. Ifra, is it clear?
Yes, sir.
So from where you have got just 1.
Sir, I haven't squared the area and then the force which is acting in second, I have also taken it wrong.
Okay. You may solve this particular question according to this diagram as well. Let me define you how to approach. Suppose you have first this wire and second this wire. There is a force along this direction as 5F. So there will be a reaction to this particular force opposite to it along this direction. So you have given only 3F at this point. So there will be 2F also along this direction. So we would draw like this. Next is 2F acting at this point. So there will be reaction force to this, which must be acting at this point like this. Now check net force at this point will be 3F as it is. So the total force for this segment will be 5F and total force for this segment will be 2F. Is it clear?
Yes, sir.
So you may use this concept to find a stress on the either wire. Any doubt?
No, sir.
Okay. You have written?
Just a minute, sir. Done, sir. Yes.
Now the next type of this deformation is tangential or shear. Suppose you have a cylindrical body base is fixed. Now, if you apply deforming force on this end to deform it along this direction, so that top face may give shift along this direction. On applying this force tangential to this particular surface, let's say area of this surface is A, and there is shift from this point to this point as X. Length of cylinder is L, and bending is just theta. So tangential or shear stress related to this is equals to amount of tangential force acting over the surface per unit area is called shear stress. Corresponding deformation is called shear strain. So it is equal to just theta. And you must have learned for small angle, sine theta, tan theta, and theta are equivalent to each other. So theta will be equals to perpendicular by base like this. So x by L. Now, if you divide these two terms, or the ratio of stress to the strain in this part is called shear modulus. So it will be equals to ratio of shear stress to the shear strain. Shear modulus is denoted by capital G. Shear stress is F tangential over area of cross section, and shear strain is theta. You may rearrange it like this. Now, in this deformation, there is change in shape of this particular object. So you will say this shear modulus is also called elasticity in shape. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Suppose a cube of side 10 centimeter whose base is fixed. A force of 20 kilonewton is applied on its top tangentially. Find stress. Second, shear modulus if shift in its phase is 1 mm. Suppose this is a cube. On applying deforming force to its top, there is bend in this shape from this point to this point. This amount of bending is 1 mm. Length of side is 10 centimeter. Applied force is 20 kilonewton. Just put all the values and try to find these terms.
Okay.
Good, Afra. Okay, good. Suppose this is cylindrical body whose base is fixed. Now, if a deforming force is applied on this direction, so it may get shifted along this. Let's say shift in this position from this point to this point is theta. Then find longitudinal and shear stress. Let's say area of this particular surface is A. Ifra, any doubt? Let me define you about this part. Suppose this is A and this is the deformed part from this point to this point along this direction. So the area of a strip from this point to this point is A and this is theta. So this area will be A by cos theta from this point to this point. Is it clear?
Yes.
Similarly, for force, this is your deformed face and this is applied force over this. This is theta. So if you draw a vertical line to this theta will be equal to this part. So this will be equal to this term. So there will be a component of force along this direction, F cos theta, and another along this direction as F sin theta. Is it clear?
Yes, sir.
Now, for longitudinal stress, we must need perpendicular force to that particular surface. So longitudinal stress equals to perpendicular force over this particular surface is F cos theta divided by area of cross section A by cos theta. So cos and cos will become cos square. So it will be F cos square theta by A. Is it clear?
Yes, sir.
Then what will be about shear stress? Force should be tangential to this particular surface. So which component of force is behaving at tangential?
So F sin theta.
Good. So for shear stress, F sine theta divided by area of cross section. So it will be A by cos theta. Cos theta will move to numerator. So it will be F by A into sine theta into cos theta. Now multiply it by 2 and divide by 2. So it will become F by 2 times of A, 2 sine theta into cos theta. And you must have learned about this formula. It is equal to sine of 2 theta. Is it clear?
Yes.
So you may write it as F by 2 times of A into sine of 2 theta equals to shear stress.
Done, sir.
Okay. Third part is volumetric or hydraulic. Suppose you have a spherical body like this. On applying deforming force from all of its sides, there will be deformation in volume like this. So initially it was at this point, V initial, and now it is at this point, V final. And next, this force is normal to this particular surface. So force per unit area, when it is normal to the surface, is also called pressure. So first is volumetric stress. So force perpendicular by area of cross section. Force perpendicular per unit area is also called pressure. Next, corresponding change in its volume is called volumetric strain. So it will be change in volume by initial volume. As you see, final volume is smaller as compared to initial volume. So difference of volume, that is V final minus V initial, will be negative. So there will be negative sign in this point. And now if you divide these two terms, you'll get modulus of plasticity. So in this part, it is called bulk modulus. So bulk modulus equals to volumetric stress by volumetric strain. Beta is bulk modulus. Volumetric stress is nothing but pressure by volumetric strain is delta V by V with negative sign. So it will be minus of P into V by delta V. Is it clear? Ifra, any doubt? Ifra, any doubt?
Yes. No, sir, that a network connection was low, so I was.
Okay, okay. A pressure of 20 atm changes the volume of a body by 1%. Find beta. You have pressure as 20 atm, which is not an SI unit. So pressure will be equals to 20. 1 atm equals to 10 to the power 5 Pascal. So it will be total pressure acting on this particular object. Change in volume by 1%, which means delta V divided by V into 100 is just 1%. So delta V by V equals to 1 by 100 or 10 to the power minus 2. And since on applying this much amount of pressure to that particular body, there will be decrease in volume by 1%. So there will be negative sign at this point. Is it clear?
Yes, sir.
So beta will be equals to amount of pressure applied, that is 20 into 10 to the power 5, divide by volume minus 10 to the power minus 2. And we have already negative sign in this formula. So negative and negative will cancel out. So it will be 2 into 10 to the power 8 Newton per meter square, or it will be just equal to Pascal. Since in this part, force will be perpendicular to area of cross section, so it will be termed as pressure. Ifra, any doubt?
No, sir. Done, sir.
Okay, so this is all about the first part of this chapter. I've just left you two things. First is stress strain curve, and next is potential energy stored in a wire. Okay. So
Okay.
next class, I'll define you that, and then we'll start the new chapter that is fluid. Okay.
Okay, sir.
Okay then.